GCA is the common term for a radar ground-controlled instrument approach in inclement weather. It enables rotary and fixed-wing pilots on IFR to land where approach minimums are as little as 200 feet above the field elevation, and where visibility is limited to 1/2 mile. This is under non-combat flying conditions. In tactical situations, the minimums can be a 200-foot ceiling and 1/4 mile visibility. Thus, landings are possible in areas of limited dimensions, a critical advantage in a combat zone. For a successful GCA landing, a pilot must thoroughly understand procedures and must follow orders of the controller. Both are responsible for a successful landing. What is required is strict observance of the following rules. Acknowledge and comply with instructions immediately. Acknowledge emergency instructions if clearly understood. If not understood, request a readback. Repeat all altimeter settings. Repeat all headings and altitudes except on final approach when instructed not to acknowledge further transmissions. Make all climbs and descents standard rate unless otherwise directed. Make all turns standard rate 3 degrees per second unless otherwise directed. In GCA, 2 types of radar functions are called for: Area Search Radar, ASR, and Precision Approach Radar, PAR. On occasion, the PAR and ASR are housed in a separate set with a controller for each, the PAR controller being known as the final controller. However, in Army aviation tactical use, both radar functions are usually combined in one set with a single controller. This dual-purpose radar is set for the surveillance function. It gives a 360-degree sweep of the area. Area Search Radar has a range of 1 to 40 miles. It provides azimuth and range readings, but no elevation. A turn of the knob puts the radar set on PAR. Precision Approach Radar gives elevation of the aircraft target as well as range and azimuth. It also has a range of 40 miles, but it is rarely used beyond 20. The PAR scope shows 2 presentations. The dim line in the upper half is the desired glide path. The dim line in the lower half is the on-course or center line. The elevation of the target aircraft is seen as a blip moving in relation to the glide path. A second blip, perpendicularly below, shows the aircraft in relation to the on-course line. It is difficult for the inexperienced, untrained eye to follow the target blips, especially in the case of a slowly moving aircraft like a helicopter. Animation will make the blip or target action clear. First the scope, now the glide path, the on-course line, and range markings. The upper blip or target is the radar image of the aircraft showing elevation in relation to the glide path. The lower one, azimuth of approach in relation to the on-course line. By following both blips, the controller can correct all deviations from above and below the glide path and to either side of the center line, so as to keep the aircraft on a true course to a safe touchdown. A GCA ground track will normally appear as an extended visual pattern. It will usually consist of an entry leg, a downwind leg, a base leg, and a final approach leg. This ground track pattern may vary considerably depending on the wind, weather, terrain, local air traffic conditions, and the variables in a tactical situation. Certain events occur in a logical sequence which the pilot must anticipate. The first event is the initial contact point, followed by positive identification. Then the controller issues the altimeter setting and missed approach and lost communication procedures. On the downwind leg, the pilot will be issued approach information that would include active runway, wind direction and velocity, and current weather. The pilot will next be directed to perform a landing cockpit check. And if necessary, pattern corrections will be given. And in addition, the controller will keep the pilot advised of his position in relation to the airfield while on the downwind and base legs. After turning to the final approach leg, the pilot is advised of the time to glide path intercept, and a recommended rate of descent may be given. When the glide is intercepted, the pilot will be advised to begin his descent. From this point to final touchdown, the pilot will be informed at each mile of his distance to touchdown point. Also during this time, the pilot will be issued constant control instructions to enable him to remain on glide path and course. Let us now follow a ground control approach in a conventional IFR situation. It begins with the pilot requesting a GCA contact from the tower.
Smith approach control, this is Army Copter 169060.
169060, this is Smith approach control, over.
Smith approach 960, request GCA, over.
Roger, 9060. Contact GCA. Frequency 256.5.
960, roger. Smith GCA, this is Army Copter 169060. Approximately 5 miles south of Smithfield, heading 360. Altitude 3000. Request GCA, over.
Note that the pilot immediately gives his position, heading, and altitude.
Army Copter 169060, this is Smith GCA. Possible radar contact 5 miles south of Smithfield. Turn right, heading 045. Maintain 3000 for positive radar identification.
960. Right, heading 045, maintaining 3000.
Unless the pilot is over a known navigational point, such as a non-directional beacon or VOR, the pilot will be given a turn of at least 30 degrees for positive radar identification. This turn brings the pilot into the entry leg.
9060, this is Smith GCA. Radar contact 4.5 miles south of Smithfield. Smith altimeter 2990, over.
960. Roger, altimeter 2990.
9060, this is Smith GCA. Continue heading 045, descend and maintain 2000, vector to downwind.
960. Roger, continue heading 045. Descend and maintain 2000. Departing 3000 at 15.
Note that the altimeter setting is given very early in the approach procedure. That each instruction changing course ends with an explanation by the controller. In this case, the explanation is that the pilot is being vectored toward the downwind leg. Recommended but not required is missed approach, but a must instruction is the lost communication procedure. Normally, these are given in combination, but may be issued separately.
9060, this is Smith GCA. If no transmissions are received for 2 minutes in the surveillance pattern, or 5 seconds on final approach, proceed direct to Smith non-directional beacon and maintain 2,500. Execute standard ADF approach upon arrival.
960. Roger, lost communications procedures.
If there is the slightest doubt in the pilot's mind about instructions, he will request a readback.
960, this is Smith GCA. Turn right, heading 090, maintain 2000, downwind.
960. Roger. Right, heading 090, maintaining 2000.
960, Smith GCA. This will be a precision approach, runway 27. Wind 290 degrees at 8 knots. Smith weather, measured ceiling 300 overcast. Visibility 3/4 miles in light rain.
When weather conditions are at or below the highest circling minimums for the airfield, weather information must be transmitted to the pilot.
960, perform landing cockpit check.
To comply, the pilot performs his check according to operating instructions for the particular aircraft he is flying.
Smith GCA, landing cockpit check completed.
960, this is Smith GCA. Turn left heading 080, maintain 2000, pattern correction.
960. Left heading 080. Maintain 2000.
Aircraft deviations from the initial approach pattern are corrected by the controller as needed.
960, Smith GCA. Turn left heading 360, descend and maintain 1500, base leg.
960. Roger, left heading 360. Descend and maintain 1500.
960, Smith GCA. Your position now 6 miles east-southeast of airfield. Stand by for left turn to final.
960. Roger, position.
While the aircraft is in a surveillance pattern, the controller must give the pilot a position report at least once prior to the start of the final approach.
960, Smith GCA. Turn left heading 270, maintain 1500, final approach.
960. Roger, left heading 270. Maintaining 1500.
The pilot should decelerate to the desired airspeed before intercepting the glide path. He maintains this airspeed till he makes visual contact with the ground or executes a missed approach. When the controller puts the pilot on final approach, he adjusts his set from area search radar to precision approach radar. On those occasions where ASR and PAR are handled separately by two controllers, the pilot is instructed to contact the final controller on a specified frequency for continuation of the final approach. The final talk-down begins.
960, Smith GCA. Now on final approach, do not acknowledge further transmissions. 5 miles from touchdown, intercept glide path in approximately 45 seconds.
The controller now transmits every 5 seconds, giving distance at least once every mile, position in relation to the on-course, and position in relation to the glide path, and making all necessary corrections.
You are now 4 1/2 miles from touchdown. Drifting slightly left of course. Turn right, heading 272. Left of course, now correcting. Intercept glide path in 10 seconds. Turn left, heading 270. Now intercepting glide path. Begin descent. You are now 3 miles from touchdown, going slightly above glide path. Adjust rate of descent. 270 the heading. Approaching glide path. Now on glide path. Resume normal rate of descent.
Approximately 2 miles from touchdown, the controller will transmit the tower's clearance to land, continuing his talk-down virtually without pause.
1 mile from touchdown. On course, on glide path. Over approach lights, on course, on glide path. Over landing threshold, approaching GCA touchdown. On course, on glide path. Now over touchdown, take over and land. Contact Smith Tower. Frequency 248.4 for further instructions. GCA standing by.
Although the controller talks down the aircraft to a theoretical touchdown point, it is the pilot's responsibility to execute a missed approach if he is not broken out visually at authorized minimums. Under certain circumstances, the GCA procedure may be modified. This is the case when the directional gyro malfunctions and the pilot does not get any readings on his heading indicator. When the pilot tells the controller he must make a no-gyro approach, he will receive information on runway, wind, and weather, as always, plus the usual orders on missed approach, lost communication procedure, and landing cockpit check.
960, this is Smith GCA. This will be a no-gyro precision approach, runway 27. Wind, 290 degrees at 6 knots. Smith weather, 300 over.
The main difference is that the controller regulates the turns the pilot makes.
Make standard rate turns. Execute turn instructions upon receipt.
960. Roger.
960, this is Smith GCA. Turn left.
960. Roger. Turning left.
Stop turn.
960. Roger. Stopping turn.
After the pilot has turned onto his final approach, the controller will order him to make all turns at half standard rate.
960, your position now 5 miles from touchdown. Do not acknowledge further transmissions unless requested to do so. Make all turns at half standard rate.
The controller then continues to talk down the aircraft in the prescribed manner until touchdown or a missed approach is executed. Sometimes the malfunction may take place at the controller's end. When the precision approach radar does not function, the final as well as the initial approach must be made on area search radar. ASR is less accurate than PAR, so higher minimums must be observed. A 400-foot ceiling and visibility of 1 mile or more. Course guidance will be normal, except that on final approach, the controller is unable to give glide path information. Instead, he will recommend altitudes for each mile of the final.
Visibility, 2 miles in light rain. Smith altimeter, 29090. Recommended altitudes will be furnished each mile on final. What will be your airspeed on final?
960. Airspeed on final, 80 knots.
From the airspeed, the controller will figure out a recommended rate of descent. The pilot must then adjust his rate of descent in line with the recommended altitudes. Also, in a surveillance approach on final, the controller's instructions on lost communication procedure will allow for more time between transmissions.
960, your position now 6 miles east of airfield. If no transmissions are received for any 30-second period while on final, execute missed approach.
960.
Roger. Lost communications.
When the aircraft is on final approach, the controller will give advance notice of when descent is to begin and the recommended rate of descent.
960, you are now on final. 5 1/2 miles from end of runway.
The pilot will maintain 2,000 feet and prepare to begin descent in 1/2 mile. GCA recommends 400 feet per minute, and he does not need to acknowledge further transmissions unless requested.
960, 4 1/4 miles from end of runway. Begin descent.
From the point where descent begins to 1 mile from end of runway, the controller will give the pilot instructions on heading and position in relation to the on-course, range, and recommended altitude at least once per mile.
Niner 60, 4 miles from end of runway. On course, altitude should be 1,900.
If the indicated altitude is not the one recommended by the controller, the pilot will compensate by increasing or decreasing his rate of descent.
Niner 60, 3 miles from end of runway. Altitude should be 1,500. You are drifting left of on course, turn right. Heading 274. Left of course, now correcting. 2 miles from end of runway. Altitude should be 1,100. Tower has cleared you to land. You are now 1 mile from end of runway. If runway not in sight, execute missed approach. Acknowledge.
Niner 60. Runway in sight.
Contact tower. Frequency 248.4 for further instructions. GCA standing by.
Smith Tower, Copter Niner 60. Request you cancel my IFR.
The three types of approaches just seen, the precision, surveillance, and no gyro GCAs, may be modified to varying degrees in a tactical situation. In a tactical situation, the visual pattern of the ground track may be drastically changed or reduced to avoid areas of enemy concentration and to reduce the total time length of the GCA. If there is an enemy position here, the pilot should be prepared for extreme modifications of the surveillance pattern. A very short final approach, a steeper glide path, and a faster rate of descent than in a non-tactical situation. Orders and information follow standard GCA procedure, but are greatly compressed in time. Also, the item over approach lights is omitted. For a brief, swift final approach, the glide path angle may be increased from a normal 3 degrees to as much as 8 degrees. The rate of descent may be speeded up to as much as 1,000 feet per minute. These conditions of accelerated, steeper movement, plus the reduced minimums of a 200-foot ceiling and 1/4 mile visibility, oblige the pilot to use extreme caution. Above all, he must obey the controller's instructions instantly and with the greatest precision. Prior to beginning his descent on final approach, the pilot will be advised by the controller of his glide path angle and rate of descent.
Niner 60, you are now on final approach. Do not acknowledge further transmissions. 2 1/2 miles from touchdown. Rate of descent on final should be approximately 950 feet per minute. Intercept glide path in 15 seconds. Drifting slightly left of course. Turn right, heading 273. Left of course, now correct. 2 miles from touchdown. Now intercepting glide path, begin descent. You are going well below glide path. Just rate of descent. 273 the heading. Approaching glide path. Now on glide path. Resume normal rate of descent. 1 mile from touchdown. On course. On glide path. On course. On glide path. Approaching GCA touchdown. On course. On glide path. Now over touchdown. Take over visually and land. GCA standing by.
We have seen an Army aviation pilot make several GCA approaches under various IFR conditions. Let us review the rules any rotary or fixed-wing pilot must follow for a successful touchdown. Acknowledge and comply with instructions immediately. Acknowledge emergency instructions if clearly understood. If not understood, request a readback. This is especially important in the case of missed approach and lost communication procedure. Repeat all altimeter settings. Perform landing cockpit check prior to final approach. Repeat all headings and altitudes, except on final approach, when instructed not to acknowledge further transmissions. Make all turns standard rate, 3 degrees per second, unless otherwise directed. This is especially important in the case of a no gyro approach, when the controller will give the orders to initiate a turn and to stop a turn. In a surveillance approach, be sure to follow the controller's recommendations on altitude. Make all climbs and descents standard rate, unless otherwise directed. Above all, remember that prompt, precise cooperation with the controller in a ground control approach is the key to a safe landing for yourself and your aircraft. Listen, understand, comply. Ceiling 400 feet. Overcast. Visibility 1/2 mile. Light rain with fog IFR weather. Only a few years ago, urgent rotary wing missions might have been delayed for hours or days. But today, most Army helicopters are equipped for IFR flight. The navigation equipment in your aircraft is both accurate and reliable. If you're skilled in the use of this equipment, helicopter operation can continue in almost any kind of weather. ADF, the Automatic Direction Finder, is one of the most widely used systems for aerial navigation. Its working principle is quite simple. On the aircraft, there is a special radio antenna consisting of several loops of wire. This loop antenna is the heart of ADF. It receives the radio signal in code from the radio beacon transmitter in a special way. In order to show how this system works, we will operate the loop antenna manually. Notice what happens when the loop antenna is turned. When the loop is parallel with a line through the transmitter, the unmodulated signal is now heard loud and clear. We will turn the loop so it is at right angles again to the line through the transmitter. The unmodulated signal fades and is completely unheard when the loop is at right angles with the line through the transmitter. The loop position where the unmodulated signal is not heard is called a null. Let's see how the ADF equipment operates manually. First, we replace the loop antenna with the radiomagnetic indicator. Normally, the RMI has 2 pointers, but for purpose of clarity in this scene, we will eliminate the number 2 needle. When the ADF is set on the frequency of the beacon, it automatically causes the number 1 arrow of the indicator to point to the transmitter. We need not go into the electronics which make the ADF seek and point to a transmitter, but there is one feature we should understand. When the loop antenna is at right angles to a line through the transmitter, how does your ADF know whether the transmitter is in this direction or in exactly the opposite direction? The equipment designers have solved this problem by using two antennas on the ADF. The loop antenna and another antenna called a sensing antenna. When a sensing antenna and a loop antenna are used, the loop antenna only has one direction in which it can detect a null. You are assured that the transmitter is in this direction and not in the reciprocal 180-degree direction. The automatic direction finder, as its name implies, seeks out and points to the selected transmitter automatically. If there is a transmitter within range and the ADF is tuned to its frequency, the loop will automatically rotate, seek the null position, and lock on. The direction of the transmitter from your position is shown on the indicator. As you continue in flight, the ADF remains lock on. The indicator needle moves to show the constantly changing direction to the transmitter. VOR is not widely available in overseas areas or in combat. In many areas, ADF is the only radio navigation system available. A second good reason can be seen on this chart. Suppose you were coming down from Montgomery on Victor 7 en route to Low. Since there is no VOR at Low, a transition to ADF is necessary. In similar situations, a transition to ADF must be made. There are many radio transmitters which can be used with ADF. On navigational charts, their symbol is a brown dotted circle surrounded by a circular shaded area. Their name is given, as well as their identifier, both in letters and in Morse code. The number shown indicates the radio frequency on which the transmitter operates. When a frequency is underscored, it indicates that the beacon has no voice transmission. Your ADF equipment is capable of receiving frequencies in the lower and medium frequency ranges, from 190 kilohertz to 1750 kilohertz. Radio beacons are also referred to as non-directional beacons. Some are established and maintained by the FAA specifically for use with ADF. The equipment is normally housed in a small semi-portable building. The transmitter is serviced periodically, but is otherwise completely automatic. The antenna is simple and transmits a non-directional signal. It broadcasts the beacon identifier in code. Regular radio beacons are found in three classes according to the power of their signal. Class MH, Class H, and Class HH. Class MH beacons have a range of approximately 25 miles. Class H, a range of about 50 miles. And Class HH, about 75 miles. The class of various beacons may be found in current navigation publications. In addition to radio beacons, commercial radio stations may also be used for direction finding with ADF. Now let's take a look at the ADF equipment on your aircraft. The loop antenna is protected and streamlined by a plastic housing. Located under the lower fuselage is the sensing antenna. On the left side of the aircraft is the electronic equipment compartment where the ADF receiver is situated.
Like all receivers, it detects and amplifies the desired signal. As an aviator, you are mostly concerned with the cockpit items. There are only two, the RMI, or radio magnetic indicators, on the instrument panel, and the ADF control panel on the pedestal. We'll deal with the control panel first. The controls are used for tuning the ADF receiver and selecting its various modes of operation. On the lower left of the panel is the control unit function switch with a volume or gain control. The function selector switch has 4 positions. In the ADF position, both the loop antenna and the sensing antenna are connected to the ADF receiver, and the equipment functions in its automatic mode. In the antenna position, only the sensing antenna is connected. And in the loop position, only the loop antenna is connected. As we proceed, we will see how each function switch position is used. With the switch in loop position, the ADF will not operate as an automatic direction finder. You must rotate the loop antenna by moving the loop switch. You rotate the loop antenna until a null is located. Remember, however, that when only the loop antenna is used, the RMI arrow may be pointing to the station or directly away from it. Without the sensing antenna, the loop cannot tell the difference between to and from. As we have learned, the frequencies on which ADF operates are from 190 kilohertz to 1750 kilohertz. On this range switch, the frequencies are shown in kilohertz. ADF is most frequently used in the automatic mode, with the function switch in the ADF position. But occasionally, with heavy static, it will be difficult to identify a station. The signal-to-noise ratio can be greatly improved by using the antenna position so that only the sensing antenna is connected to the receiver. After the station has been identified, return the function switch to ADF and proceed with fine-tuning using the Tune to Max meter. The final control on the ADF panel is the BFO, or beat frequency oscillator switch. The BFO is only turned on when tuning a station which transmits an unmodulated signal. When unmodulated signals are encountered, the ADF will seek the station, but no identifier will be heard until the BFO is turned on with the function switch in the antenna position. Now you can hear the identifier. You will not find many stations which transmit an unmodulated signal in the United States, but they are quite common in Europe and other parts of the world. Unmodulated signals are also called A1 type emission. When you see this note, you will have to use your BFO with the function switch on antenna to identify the station. The ADF control panel is simple and easy to operate. Proficiency in manipulating it comes quickly with practice. On the instrument panel, there are 2 radiomagnetic indicators, one for the pilot, the other for the co-pilot. On the RMI, there is a switch labeled VOR ADF. The switch must be on ADF when ADF is used. The rotating compass card is slaved to the aircraft gyromagnetic compass and constantly shows the aircraft's magnetic heading under an index at the top of the dial. Remember that the RMI has 2 arrows or pointers. The thin one is called the number 1 or ADF arrow. The wider arrow is used when VOR is connected to the RMI. The ADF arrow indicates the actual magnetic bearing to and from the beacon to which the ADF receiver is tuned. On older types of ADF indicators, a relative bearing was shown. This required mental arithmetic to convert to a magnetic bearing. With the RMI, this mental step is not necessary, except when the aircraft's gyro compass is inoperative. Now that we are familiar with ADF theory and equipment, how is it used? There are 5 basic procedures in which ADF is used. Position fixing, track interception, tracking, holding, and approach. Master these 5 techniques, and you have mastered ADF. First, position fixing. All aviators should know their general location at all times. But in instrument flight, you must be able to determine your exact location at any time. Here's how you use ADF to pinpoint your location. You know your position to be somewhere north-northwest of Cairns. You can use the Brantley radio beacon and the Enterprise radio beacon to find out exactly where you are. The frequency of the Enterprise beacon is 308. The ADF is already turned on and warmed up, so you can proceed to tune the Enterprise frequency. Check that the function switch is set to ADF, then select the proper band for 308 kilohertz. Turn the tuning knob to show 308 kilohertz onto the index line. You will hear the beacon's identifier in your headset. While observing the tune to max meter, fine-tune with the tuning knob. Normally, you can easily identify the beacon. But if signal strength is weak or there is static, switch to the antenna position to get a better signal-to-noise ratio. Then back to ADF to make sure the bearing reading on the RMI is reliable. Proceed as follows. Move the loop switch to the right and watch the number 1 needle move clockwise. When it has gone approximately 30 degrees, release the loop switch. If operation is normal, the needle will immediately return to the original heading. You find that the direction to the beacon is 200 degrees, and the direction from the beacon is 20 degrees. You transfer this information to your chart by drawing in a line at an angle of 20 degrees from the Enterprise beacon. The direction from Enterprise to you is 20 degrees, and the direction from you to Enterprise is 200 degrees. To draw the line, you must use the 20-degree reading from the station, since you don't know what your own location is. Next, you turn to a heading of 200 degrees toward Enterprise. Then tune the Brantley beacon. You get a reading on the number 1 needle of your RMI of 270 degrees to the beacon and 90 degrees from the station. On your chart, you sketch in a line of 90 degrees from Brantley. Now your position is fixed. You are located where the 2 lines intersect. You are next told to proceed to the Enterprise beacon via the 180 magnetic course to Enterprise. To do this, we use the next basic procedure, track interception. The objective is to establish yourself on the 180-degree magnetic course to Enterprise. You should immediately retune to the Enterprise frequency from the Brantley frequency. Your present heading is 200 degrees to Enterprise. To gain a 180-degree course to Enterprise, first turn to the left until you obtain a reading of 180 degrees under the heading index of your RMI. This puts you on a 180-degree magnetic heading, parallel to your desired course to Enterprise. Until you have gained proficiency, it is best to gain a parallel course first. Later, as skill develops, you can eliminate this step. Paralleling makes it easy. You check your RMI and note that the number 1 needle is to the right of your heading. You know you must turn to the right. You'll never be confused if you remember always turn toward the needle. First, you will intercept at an angle of 45 degrees. What heading should you assume to intercept at 45 degrees? When you're flying a parallel course, it's easy to calculate. For an interception to your right, you simply determine your heading 180 degrees and add 45 degrees. Your interception heading is 225 degrees. When the track you wish to intercept is to your left, you subtract 45 degrees. Your intercept heading is 135 degrees. Remember, right, add. Left, subtract. As you turn right 45 degrees to a heading of 225 degrees, the ADF needle will move toward your desired course. Note that the desired on-course heading is aligned under the first 45-degree index left of the heading index. These indices are on the RMI to be used for this purpose. Continue to monitor the ADF needle until it indicates 180 degrees. Then turn smoothly to the left until your heading and the ADF needle both read 180. You have intercepted the desired course. Now all you have to do is fly a straight track to Enterprise. With no wind, flying a straight track is easy. But suppose you have a fairly brisk crosswind from the southeast. With a proper understanding of ADF tracking procedure, crosswind compensation is not difficult. Maintain a magnetic heading of 180 and monitor the RMI. The ADF needle gradually moves to the left, indicating that the wind is from the left. You will have to crab to the left, into the wind, but don't do so until the ADF needle shows a 5-degree off-course deflection. At this point, your situation will look like this. Your heading index reads 180, but your number 1 needle reads 175. You make an initial wind drift correction of 30 degrees into the wind to a magnetic heading of 150. Maintain this heading until your number 1 needle again reads 180 degrees. Then take out half of the 30-degree initial correction by turning 15 degrees in the direction of the original heading. This may turn out to be the proper angle of crab, but let's say that after a few minutes, you note that your number 1 needle reads 185 degrees. You have too much wind drift correction. Return to your original heading of 180 degrees, and then allow the wind to blow you back on course. When your ADF needle again reads 180, turn into the wind approximately half of your last correction. This procedure, called bracketing, can be repeated until a proper drift correction is determined. With a 7-degree crab, you proceed until station passage at Enterprise is noted. Station passage can be anticipated when the ADF needle fluctuates. Shortly, the needle reverses, and you are directly over the station. 4 things must be done at this time. The 4 T's: time, turn, tune, and talk. You note the exact time of station passage. Turn to your new track if necessary. Tune the ADF ahead to the next radio beacon. And talk to the controlling agency to report station passage. Frequently, when beacons are a considerable distance apart, you will not tune immediately to the next beacon. You will remain tuned to the same beacon and track outbound. The same tracking technique is used, reading the reciprocal of the original course under the tail of the needle. At Enterprise, a turn is made. Your intention is to intercept the 086 magnetic course to the low radio beacon. You again use the bracketing procedure to determine a magnetic heading which will make good the 086 course. The next procedure with which ADF can be used is holding. prior to reaching low, you are told to hold southwest of the low radio beacon on the 059 magnetic course to the beacon. To make left turns, and you are given an expected approach clearance time. As you move toward the low beacon, you work out your plan for entry into the holding pattern. Since you will be arriving at less than 70 degrees of the inbound course, a left turn outbound will be required. Knowing the effect of the crosswind, you estimate the magnetic heading required to make good a 59-degree inbound course. As you approach low radio beacon, you start to get station passage indications. When the needle reverses, note the time of station passage, then start your left turn toward the outbound course and report holding. The first point where an ADF indication is important occurs just as you roll out on the outbound leg. Now you should be abeam the beacon. The ADF needle will be 90 degrees left of the required course. At this point, you start your timing for the outbound leg for 1 minute. ADF indication becomes important again as you roll out on the inbound course. Start your timing and adjust heading for the 059 track. You continue to use previous wind experience and apply corrections throughout holding if necessary. As station passage is indicated, note the inbound time, and if it is not 1 minute, adjust the subsequent outbound times as necessary. On your turn to the outbound heading, continue until the abeam the station indication is noted. Now we can see that there are 3 times in holding when ADF readings are important. First, when the helicopter is abeam the beacon and outbound timing is started. Second, rolling out onto the inbound leg and proceeding to the station. Third, when station passage is indicated and the outbound turn is started. Proper ADF readings at these points will assure that you are satisfying the holding pattern requirements prior to your expected clearance for the approach. This takes us to our final basic procedure approach. When given approach clearance, while holding, you immediately start a descent to procedure turn altitude. Prior to this time, your entire descent should have been planned, and you should be thoroughly familiar with the approach chart and missed approach procedure. When approach clearance has been received, the 1 minute holding limitation is eliminated. You may elect to extend the outbound leg to provide more time for the descent or to extend your time inbound. When making an approach from holding on the final course, the turn inbound becomes the procedure turn. When you have established yourself on the approach course, you may start your descent to low station altitude while making necessary crosswind corrections to maintain approach course. A wind shift will very likely be encountered as you approach the ground. Prior to station passage and at low station altitude, you must be well established on course. Over the beacon, start your time as the needle reverses. Now readings are used at the tail of the needle en route to the airfield. After your descent is started, the report inbound is made. Before the missed approach time has elapsed, visual contact should be achieved. If not, the prescribed missed approach procedure must be started. Seeing the runway coming up where it should be is always satisfying. But remember, IFR missed approach procedure is an exceedingly important part of ADF approach. Before you even start, you must be sure you know what to do if missed approach is necessary. Now, how much have we learned about ADF? We know that ADF depends for its operation on a loop antenna, which, because of its highly directional characteristics, can seek and point to a radio beacon. There are many radio beacons which can be used with ADF. Any transmitter which broadcasts in the frequencies between 190 and 1750 kilohertz can be used. To use your ADF, you have a control panel which is compact and well designed, and a radiomagnetic indicator which displays both aircraft magnetic heading and actual magnetic heading to the beacon tuned. There are 5 basic procedures in which you will learn to use ADF. Position fixing makes it possible to locate yourself precisely at any time. Track interception provides a simple and accurate means of moving to any course to a station. In tracking a course, the ADF makes precise crosswind correction simple. In holding, ADF provides a simple means of maintaining a desired pattern. Approach must be pre-planned as to wind effects and estimated ground speed. Precise tracking with ADF is essential. Understanding of the principles involved in these basic procedures and concentrated attention during dual instruction will give you confidence when you fly IFR.